So one of the ways that the existence and uniqueness theorem is most useful to us doesn't come right out from the way it's formatted, the way the theorem is spelled out for us. So a particularly useful way of saying this is if two solution curves ever pass through the same point on the slope field of a differential equation, right? Two solution curves for a differential equation ever pass through the same point on the slope field of a differential equation, then what does that mean? Well, think about what that would imply. That means you'd have two things moving through a slope field and they happen to cross at a particular location. But we know the slope field curves don't allow for that. So the existence and uniqueness theorem guarantees that they must be the same curve. So think about what this is saying. If you have two solution curves that are following the slope field and they happen to cross at a point down here, then they must actually just be the same curve, because you can't cross slope field lines. You can't cross on a DE plot. You can't have two solutions that cross each other. So if you consider a differential equation that looks something like this, you might look at it and go, oh, yeah. Does this thing meet the bill, or does this thing fit the bill of for our existence and uniqueness theorem? And so remember, there's two requirements. And the first thing you probably want to recognize is that this is what we would call an autonomous differential equation. And we've learned a little about those, and we've seen how they work. But a couple of things to recognize is that f of y is continuous everywhere. It's a polynomial, so of course it's continuous everywhere. The other thing to recognize is that if I take the partial derivative of this thing with respect to y, taking the partial derivative of the function, it's also continuous. And so those two things together, those are the requirements. Those are the two requirements for the existence and uniqueness theorem. And taken together, this means any solution, let me scoot that over, any solution curve is unique anywhere. And we can say it's anywhere because, of course, these are continuous everywhere. So any solution curve is unique anywhere. If you give me an initial condition, it's guaranteed to produce a unique solution curve. So the next thing that we kind of remind ourselves of is, what about these equilibrium solution? What does it mean to be an equilibrium solution? And so equilibrium solutions, if you remember, that's where the derivative dy dt is equal to 0. And that happens when, and it's conveniently pre-factored for us, when y equals 2 and when y equals -1. There's two places. So what we can do is we can call these two are equilibrium solutions. I'll call this one y1 of t, and I'll call this one y2 of t. Because what it's saying is, as long as you stay on this horizontal line, you're on an equilibrium solution. Same thing over here. And just for giggles and to be able to identify what they look like, I'm going to give them a little bit of a kind of color coding. And so I'll give this guy is kind of bluish color, and I'll give this guy over here kind of a greenish color. So that when I produce my DE plot, and I did this in Maple and included it in the notes, you can see my first solution curve, the green one, is this guy right here. That's my equilibrium solution. That's y1 of t equals 2. And that's where the derivative is equal to 0. And you can see it's equal to 0 because it's a nice horizontal line on the slope field. And then, of course, the other one, this guy right here, I have to scoop my graph up a little bit to be able to see it. But you can see him, he's right here. And that's my y2 of t equals -1. And that's also where my derivative is equal to 0. And what's nice about the fact that it's an autonomous differential equation is I get to ask, well, what's happening everywhere else? What's happening above y1? What's happening up here in this region? Well, it can't have a derivative equal to 0 anywhere but here and here. So what are the derivatives up here like? Well, up here, all of the derivatives, all the slope field lines are pointing in the up direction, right? So they're all greater than 0. And so it's guaranteed your derivative is going to be greater than 0 when your y value is greater than 2. Likewise, you can say in between here, all of these slope field lines are generally pointing down. So in between our two equilibrium solutions, you're going to have slope field lines that are pointed down, so that means the derivative is negative. And that's when y is somewhere between -1 and 2. And of course you've got down here, everywhere that y is less than -1, you can see you're going to have positive slope field values. So that means positive slope whenever y is less than -1. And so what this allows us to do is, taking a look at our slope field, you can see if you give me an initial condition that is anywhere in this region up here, you know exactly how it's going to behave. If you give me an initial condition in this region here, you know exactly how it's going to behave. Its solution curve is going to behave. And same thing down here. So for example, if I were to give you an initial condition of something like, I don't know, for an IC of something like y of -2 equals 1. So that means y of -2 equals +1. So something like right there. There's my initial condition. Well, it's a little over, but you get the idea. What's going to happen to that solution curve? Well, it's guaranteed to be unique, but it's going to follow the slope field line. So as best I can, I'm going to kind of draw my slope, my curve following the slope field lines. Remember, I can't cross these slope field lines. I can't just like go this way because they are tangent lines. So I'm kind of following the curve. And then once I get here, I know it's going to ride along this solution curve. It's going to get closer and closer and closer to y equals -1, but it'll never reach it. And if I play it backwards, play the clock backwards, I can see I'm going to have a solution curve that's going to do something like this. Right? So for this initial condition, we have a guaranteed unique solution curve. And there's only one curve that ever passes through that point. Only one curve ever passes through the point -2, 1. Right? So the existence and uniqueness theorem allows us to interpret the slope field in a richer way, but it also allows us to make predictions about what's going to happen. And we don't have to worry about things like, well, if I had an initial condition that starts here, is it possible for me to go up here on that same solution curve? And the answer is no, because there's no way you can cross an equilibrium solution, because if you crossed an equilibrium solution, you would be the equilibrium solution, right? Nothing ever touches this line unless you are that line to begin with, right? So that's pretty handy to keep an eye on. And so the next page, and this is the last page of notes for this section, there's some examples, but the last page of notes for this section says, now what if we're trying to solve this initial value problem? Well, we know for an initial value that starts at a height of 1 that this is going to be trapped. This solution curve right here, that's our solution, is going to be trapped on the bottom end by -1, a height of -1, and on the top end by a height of 2. We know that the solution has got to be between these, since any solution with an initial condition between the two equilibrium solutions must remain in that region. It can't cross an equilibrium solution. So no solution curve can cross, and I'm going to put this in parentheses, or become an equilibrium solution. Solution, whoops. Right? And so the existence and uniqueness theorem guarantees this. So I'm going to write down underneath, thanks, existence and uniqueness theorem, because that is what guarantees we have only one solution curve that goes through that point, and that it's locked in vertically between these two heights. Right, we saw that on the previous page, right? We saw that when we took a look at this. If you start anywhere in this region, your solution curve is bounded by these two. You can't become those two, but you're bounded by those two. Right? So we also know a few things about the particular solution. So for example, since we know our initial condition that we're given above is y of 0 equals 1, this guy right there, we know that as t approaches infinity, y of t approaches -1, and as t approaches negative infinity, y of t approaches 2. Sorry. And that's guaranteed by the existence and uniqueness theorem. And that's because we know all solution curves in this region have negative slopes. They have to, right? And if you think back to the example at the beginning of this section, they have to have negative slopes because there's 0 slope right here, there's 0 slope right here, and those are the only places where the slope is 0. So in between, it can't be 0. It's either got to be positive or negative, and since we're seeing that they're all negative, you don't have a choice. It has to be negative. You can't change signs like that without becoming 0. And of course, we already know where the slope is 0, those equilibrium solutions. Okay, so the last 2 pages for this section are 2 examples. You'll notice this is from the textbook. That's page 71, number 2. And the other example, the next example, if I can get the page to flip here, is page 73, number 16. And these are both examples that I want you to give a shot at solving. And what I'll do is I'll scan them and I'll post them, make those available for you to be able to check your work. But it's a good chance to kind of check your understanding and make sure you kind of make sense of what's going on. But that's it for section 1.5.